Good morning. Please confirm whether I am audible.
Yes, sir.
Yes, sir.
Right. And you can see the numerical or extra day summary on screen.
Yes, sir.
Okay. Right. So first of all, I'm sorry again today because there was no power supply from this morning, and just it resumed. So it took long time to get my laptop boot for the first time today. All right. So we'll just summarize a few things from yesterday. Yesterday we have started the design of a shaft, and a few equations we have looked into. Those equations were the equations which you required to design the shaft. So we have seen different cases. The case, this is one case, shaft subjected to bending moment only bending moment. So we derived one equation, okay, from some basic formula which you know, m upon I is equal to sigma b by y is equal to E by R. From that equation, which is called as a flexural formula, we came to know that sigma b bending stress can be found as 32 bending moment divided by pi d cube. We equate this sigma b to permissible given by SYT by factor of safety, given by SYT by factor of safety, equal to 32 mb divided by pi d cube. Mb, that is bending moment. Of course, this is always a maximum bending moment wherever it occurs, that you have to find out. Once we put into this equation, we get the d unknown. So this way we can find out the shaft diameter. Second case, we are also seeing if it is subjected to only torque or torsional moment. That torsional moment, somehow that torsional moment is known to you, either by power and RPM or by any means. We know the torsional moment the shaft is subjected to. If we put this torsional moment here, then 16 mt upon pi d cube is equal to tau. Tau is again induced stress. We equate this to permissible. Permissible is given by 0.5 times SYT by factor of safety is equal to 16 mt upon pi d cube. We can find out the T. This equation gives you the diameter when the shaft is subjected to only torsional moment. Then we had seen two more equations when shaft subjected to combined bending and torsion. So it means there is existence of some maximum bending moment which you know, and there is existence of some torque which also know. This also in maximum, of course, if there are variable quantities, maximum torsion we have to put. If these two loadings are simultaneously acting, then we have to find out the principal stresses, which are given by sigma 1 and tau max rather. So sigma 1 is equal to 16 upon pi d cube under root in bracket mb plus under root mb square plus mp square. How it is derived, we have seen yesterday. I also put the same yesterday lecture on YouTube. You can go to that also if you want to revise yourself. So if we know the bending moment value, the torsion moment value, and if you correspondingly, if you equate this to SYT by factor of safety, and this you equate if to 0.5 SYT by factor of safety, you get D unknown, that you can find out D. So you get one D from sigma 1 equation, another D from tau equation. Whatever maximum you get out of these two, that will be your answer. The entire procedure which we described so far This procedure is called as a design procedure. Design on the basis of strength. Design on the basis of strength. Why it is on the basis of strength? Because we equate it to permissible strength. We equate it to permissible stress. That's why. That's why it is designed on the basis of strength. There are other methods also in the shaft design. One of the popular methods is shaft design by ASME code. ASME, that you know, stands for American Society of Mechanical Engineers. This body, this organization has put forth one code. Code is one standard procedure, a set of instructions. If you follow that instruction for any design, say, then nobody will object you because that is some standard design process. So there is one separate procedure for shaft design. What is that? As per the ASME code says that maximum permissible shear stress. Actually, not permissible. Permissible is not what to be used here. I'll use here maximum stress. Maximum shear stress induced in a shaft if that shaft is subjected to some value of bending moment and some value of torsion moment. Then the tau max is given by 16 upon m pi d cube under root kb mb square plus kt mp square. Kb mb whole square plus kt mp whole square. Now, if you see this equation and this equation which is given by ASME, and the equation which you are derived yesterday of tau, this equation is almost similar, except there is kb and kt involved here. Okay. Now, what is kb and kt? kb and kt are called as, kb is called as combined shock and fatigue factor. Combined shock and fatigue factor applied for bending moment. This is called as a combined shock and fatigue factor applied for bending moment. Now, you will ask the question that why it is required, what it takes into account. The answer is given in the definition itself. This is combined shock and fatigue factor. Now, we know whenever the machine starts, suppose if other day, if you know that there is a machine is there and there is a shaft, and a shaft is subjected to some amount of torque. Let us say some 20 kilonewton meter. Okay. Now, for an entire duration of time, if your operation is almost same operation means, suppose if you are cutting some material, okay, tool forces are there. So load is same, so RPM is same, and that's why torque is same. So imagine one situation when the torque on the shaft is same. This is what I am drawing. Torque. This is torque. MT. Torque is same for all time. T for time. But it doesn't happen this way in practice. Whenever you start the machine or you stop the machine, there is a jump in the requirement of the torque. So torque, instead of this figure, I will say the figure is actually something like this. This way. It means during the starting of the machine, there is a large amount of torque required. Now, what this is, this condition we call it as a shock. Say, shock. Shock is nothing but some loading, instantaneous loading of large magnitude is a shock. So this is something shock, and obviously you want to take into account this torque also. This definitely you will take into account this torque while designing, but this also you want to take into account because during starting it will require a high value of torque. right? Same is the case with the bending moment. And therefore, to take into account the shock, this KB and KP are introduced. Another word is fatigue here. Fatigue is what? Fatigue is what? When you do the same work, in repetitions, your efficiency gets reduced. In general, this is not a technical definition of a fatigue, but fatigue is what? In normal day-to-day language we use word fatigue. Fatigue is what? When you do some work in repetitions, repeatedly if you do some work, okay, your efficiency of doing the work somehow gets less. Okay, and that's why you need a change. That's why always you say that I need some change. So this analogy, if you apply to fatigue, this technical word fatigue is what? This, suppose if this is one shaft rotating, and this is applied with some forces. There are some forces are there. What happens because of if you see at this instant, this is say fiber A, this is say fiber B. At this instant, this will bend like this. It means this A fiber is in tension, B fiber is in compression. Sorry, A fiber is in compression, B fiber is in tension. But if you just imagine that after a half revolution, see what I'm saying? After a half revolution, this fiber will be B and this fiber will be A, because after a half revolution, this will change. But the loading directions are still same. It means this will be subjected to again this type of loading now, this type of bending moment, or it will deflect this way. But now this is B and this is A, which is opposite to the previous case. So now in the previous case, before half revolution, A is in compression, B is in tension, whereas here A is in tension, B is in compression. Okay. This type of alternation, if alternating load, if you observe, the strength of the material gets reduced. This is called as the fatigue. We'll see for mechanical student, there is another separate chapter on fatigue. We'll see that. But in general, this is means of fatigue. Repetitions. This is something like this, repetitions. Okay. So to take into account this reduced efficiency or say reduced strength because of this fatigue, you want to take into account the one factor, and that factor is called as now combined shock and fatigue factor applied for bending moment. So KB is combined shock and fatigue factor applied for bending moment, and this KT is combined shock and fatigue factor applied for torsional moment. The values of this KB and KT are ranging in between 1 to 2. So if it is ranges between 1 to 2, then if it is not given, then one can suitably take it as 1.5. Okay. So what we are discussing the shaft design by ASME code. As per ASME, tau max is equal to 16 upon pi d cube under root KB MB whole square plus KT MT whole square, where MB is maximum bending moment occurring at any section, MT is torsional moment, KB is combined shock and fatigue factor applied for bending moment, KT is combined shock and fatigue factor applied for torsional moment. By this way, you get the tau max. Now, again, as per ASME, this is one equation which we are seeing now. Second equation as per ASME, that tau permissible now. Tau permissible is equal to 0.3 of SYT or equal to 0.18 of SUT, whichever is minimum. So another equation which is given by ASM is what? Permissible shear stress is equal to 30% of SYT, that is yield strength in tension, or 18% of SUT. SUT stands for ultimate tensile strength. If you refer this to a simple steel stress strain diagram, you get some yielding here and you get some breakage here. This is a SYT load, SYT, and this is a SUT. Okay, right? So SUT is always more than SYT. So if for a given material, if SYT and SUT are known, you can find out the 30% of SYT and 18% of SUT, which one is minimum, that becomes your permissible stress. No need to say here, you must be knowing by this time that tau maximum induced given by this equation, permissible given by this equation, you will definitely equate these two, you will get unknown D that you can find out. Now, one more thing which is also mentioned in ASME, that if there are keyways. Now, what is keyway? Keyway is something like this. Suppose this is, say, some shaft, right? And what you want to do, you want to put one hollow shaft over it. Let us say, suppose what I am doing now. This is some hollow shafts. This one. This is a hollow shaft. This way, right? And you want to introduce this solid shaft into this hollow shaft. Okay, and you want a tight fitting. Tight fitting in the sense now that if this rotates, this also should rotate. This is your requirement. So what you do? A mechanical way to assemble these two components is to have keyways. So what is the keyway? You will have one slot here, this way, and you will have one slot here, this way. These two slots, if I see the side view of this, you will see something like this. And if you see the side view of this, you will see something like this. Okay, and if you assemble it, you will see the side view as this. Through this slot, now you can insert one rectangular element which is called as a key. This key is tapered. So wherever it tapered end you will place it here and you will hammer it from the other end. So a half part of this inside this part, shaft part, and half part is inside this hollow shaft part. This way you will mechanically assemble it. Now, problem is that whenever you cut any material, the strength of that material gets reduced. That's the universal truth. But whenever the material is cut at certain location, then this will reduce the strength of that material. Now, if its strength is reduced, this reduction in the strength because of the keyway is taken into account in the ASME. So ASME says now that if there is a keyway, then this permissible shear stress is equal to 75%. It means the strength reduces to 75%. So in a revised case now, if we consider this fact that the strength reduces because of the keyway, And by and large, you can see keyways are present almost in all components whenever you have assembly. Therefore, if this strength is reduced, and if you want to take into account that reduction in the strength, tau permissible is equal to 75% now. That is 0.75 into 0.3 into SYT, or is equal to 0.18, sorry, is equal to 0.75 into 0.18 into SUT, whichever is minimum out of these two. If you see now what is different between this set of equation and this set of equation, this set of equation is without considering the fact that the strength will be reduced because of the keyway, and this is by considering the fact that the strength will be reduced because of the keyway. So therefore, finally, I will say that if the keyways are present, the permissible stress is given by, permissible shear stress in the shaft material is given by 0.75 into 0.3 into SYT, or 0.75 into 0.18 into SUT, which is minimum out of these two. So on one hand, we get tau permissible. Previously, we know what is the maximum induced stress. So maximum induced stress and maximum permissible stress, you will equate these two. If you see unknown will be only D, you can find out the value of D, right? And in the syllabus, it is actually suggested to use ACV code. That is, by these two equations, you can find out the diameter of the shaft. There is one other way also, third way also, that is shaft design. Shaft design on the basis of torsional rigidity. On the basis of torsional rigidity. Now, what is the meaning of torsional rigidity? We'll understand if we just see one equation. The equation which you are again familiar with. You know, the equation is what? Mt upon J is equal to, yesterday we are also seeing same equation. Tau divided by R is equal to G theta divided by L, this equation. Yesterday we had seen, actually we had done some, we had derived one equation considering these first two terms. If I now take these two terms, first and the last, Mt by J is equal to G theta by L. Okay. What I get some, if I want to get some theta from this, theta is equal to Mt into L divided by J into G. If you just look at this equation, this will give you, this Mt is a torsional moment which is known to you for a given shaft. L is a length of shaft which is again given to you. J is polar moment of inertia, which actually is equal to pi by 32 to the power 4 for a solid shaft. And G is a modulus of rigidity, which is a property of a material, just like Young's modulus. You know Young modulus E, or it is also denoted as Y. And another modulus is modulus of rigidity. It is sometimes denoted as G or sometimes denoted as C. Now, if somebody asks you one question, that design a shaft when it is subjected to, design a shaft that is subjected to some torque. But now you have to design in such a way that angular twist, you know, twist is what? Angular twist. If I just extract the two sections, if I see from this end, and if I extract two sections, one section is this one, and a section which is just near to it, another section, right? If you see these two sections will have some angular deformation, angular twist. It means what? What I mean to say angular twist? If this is point A, this is point B on another section. If I superimpose these two, then I'll get A and B together at one point. But if after a twist, A point on one section and B points on another section, which was earlier at the same location, are now at different location. This means that it has twisted by some angle. That is called as angular twist. So now if a nature of asking the question or designing is that the shaft is subjected to torsional moment mt, design the shaft in such a way that angular twist should not be more than, say, some 1 degree. Angular twist should not be more than 1 degree. If that is a question, then your criteria is not a strength. You are not talking here anything like that the strength, induced strength is less than permissible. This is not your approach while designing. Your approach is you have to design a shaft in such a way that angular twist should be within limit. If that is your focus, but angular twist should not be more than permissible, then that shaft design is called as a shaft design on the basis of torsional rigidity, right? Shaft design on the basis of torsional rigidity. And that design can be found by using this single equation, this equation. Only precaution you have to take is that theta is always in radians. Theta always in radian. So you have to put theta is in radian in this equation. And therefore, if it is given in degrees, then if I write this way, theta is equal to mt upon j L upon g, mind well, theta is in radian in this equation, right? If I want to convert theta into degrees, I must convert it into, if conversion of theta to radian to degree, what you do? You multiply it by 180 by pi. Okay? So therefore, theta is equal to 180 by pi. If I multiply it by 180 by pi, it means I converted that into degrees. So theta here will be in degree. Okay? And therefore, maybe sometimes you can put j is equal to pi by 32 d to the power 4. Okay. So what I mean to say that 180 divided by pi into mt as it is, and this is equal to pi by 32 d to the power 4 into L by g. This way. What I can do that this all the terms which are numbers 180 pi, another pi here 32, all this can be clubbed together into a single number, and what you can get is 584 mt into L divided by g raised to the power 4. This is equal to theta. And this, of course, this is in degree. Okay. So therefore, if somebody asks the question that there is some torque on the shaft, length is so and so, I want to design a shaft so that angular twist should not be more than 1 degree. What I do? Simply, I will equate this to 1 degree. Okay, and remaining as it is, I can find out the value of d. This is called as a angular, this is called design of shaft on the basis of torsional rigidity. there is one more way, design on the basis of lateral rigidity. Will not go into details of lateral rigidity, but just let me give you an idea what actually it means. Design on the basis of lateral rigidity, it means a typical problem. You just see that this is something load, this is say some support ends, you can put the reactions, right? And your approach or your consideration is not whether the induced stress is less than permissible or not. This is not your criteria. Your criteria is whether the deflection is, this is the maximum deflection. The deflection is, say, not more than 2 mm. So, problem statement will be like this, that the shaft is subjected to so many forces, and thereby you can find out the bending moment maximum. Under the action of this loading, design the shaft in such a way that maximum deflection should not be more than 2 mm. If this is your way of thinking, this is your approach, then it means that you are talking about you are designing on the basis of lateral rigidity, right? So these are the various ways to design the shaft. Okay. Now I'll give you one idea of one simple sample numerical. Say this is one sample numerical I just put. This is a typical shaft design problem. With the knowledge of what we have gained so far, can we find out the diameter of the shaft that we have to look into? If the problem says that there is one electric motor, if you can see this diagram, electric motor. So this motor shaft which is coming out of this is coupled to the shaft. So this is my shaft which you want to design. This is a motor shaft. This what you see is that is it coupled the two shafts. It's coupling. This and this, these are bearings or supports in general. Distance between two bearings is given as 750 mm. This is one pulley on which a belt is passed. If you see the other view of this pulley, you see this view in which you see the belts is there. So these are belt tensions. FC1 and FC2 are shown as some belt tensions. The distance between this extreme right bearing and the pulley is, this distance is 200 mm. The problem says that there is this will of course deliver a power. Power transmitted through the shaft is 12.5 kilowatt. The shaft is running at 300 RPM, 300 revolutions per minute. The weight of pulley which is placed at C location or extreme right, you can see this location. This is pulley. Diameter of pulley is given as pulley weight. Pulley weight is given as 300 Newton. Diameter of pulley is given as 450 mm. Belt tension ratio. You also must be knowing that whenever there is a belt, I hope you know it, but still I'm here. Draw one picture. If suppose if I draw two identical diameters pulley and the belt is passing over this pulley, you must be knowing this, that one side tension is a tight side tension and another side tension is a slack side tension. Okay, so tight side and slack side tensions are there. So out of the FC1 and FC2, one is tight side, one is slack side. So that ratio, that of course that slack side tension is always smaller than tight side, and that ratio, that is TT tight side and TS slack side, this ratio is called as a limiting tension ratio, and this limiting tension ratio is given as 2:1. It means it is equal to 2. What is mentioned in here? This one. SUT of shaft material, SYT of shaft material is 300 Newton per mm square. That is yield strength in tension. And SUT of the same shaft material is 550 Newton per mm square. The combined shock and fatigue factor for bending and torsion is 1.5 and 1. This means that KB is equal to 1.5 and KT is equal to 1. No need to say that if it is KB and KT factors are given, it means that you have to design a shaft as per ASME code, because ASME only talks about the KB and KT. Determine the shaft diameter is the ASME code. So just if you imagine, if you understand this problem, one can think of the solution. The very first step in bringing out the solution is that you identify the case. What type of loadings are there? If you ask me what type of loadings are there, I will say there are two loadings. One is bending moment, because there are some forces. Only weight is there. Belt tension is there. So some loads are there. If there is any load, any point load is there, any load is there, it means that the shaft section is subjected to bending moment. How it is to find out? How it is to find out? Different thing. But you can see it. So one loading is bending moment. Another loading, which is also actually not seen somewhere here on the picture, but another loading is the torsional moment, because power is given, RPM is given. If power and RPM both are given in any problem, immediately you should tend to write the torque. Torque is equal to power divided by omega. That is, power divided by omega is 2 pi n by 60, where n is the RPM of the shaft. So if power is given, RPM is given, immediately you can find out the torque. It means torque is given. So therefore, this numerical perfectly fits into a category wherein the shaft is subjected to bending moment and torsional moment. The moment I understand that the shaft is subjected to bending moment and torsional moment both, and I want to design the shaft using the ASME code, immediately I should write two equations. One is what? One is maximum stress, and another is permissible stress. Maximum stress is given by 16 upon pi d cube under root kbmb whole square kpmt whole square, and permissible stress is given by 0.75 into 0.3. Now, why I am writing 0.75? Because I am considering that keyless are present. into SYT R is equal to 0.75 into 0.18 into SUT. SUT also given, SYT also given. We can find out this part of the equation as well as this part of the equation. You get some number from this, you get some number from this. Out of these two, you get some minimum, and that becomes my answer. So therefore, tau permissible finally will be equal to whatever number you get out of these two, minimum number out of that will be Newton per mm square, will be my permissible stress. Let us say this is now equation number 2, and this is some equation number 1, and 1 and 2 now equate. Okay. Now, of course, you have to find out torsion moment if not directly given. You have to find out the bending moment if not given. Of course, they will not be given directly. This you equate to permissible because you are equating to equation number 2. Unknown will be only D. That you can find out the value of D. So actually now, if you cannot solve number of problems, at least you can go through the statement of the problem this way and just think this way, that what is the loading given, which category it fits into, what are the relevant equations, what are the unknown things, whether MD is given or not, MT is given or not, how you can find out this MT is not given. This way you have to think it and then go on solving the numericals, go on solving the exercises. Of course, we'll see at least 3-4 numericals, complete solution of 3-4 numericals in these coming lectures also. If you simply honestly focus on all the explanation, I'm sure you will do all your exercises. Understanding is important along with your effort. If both are there, then definitely you can succeed with a very good manner in this subject. I have seen few students scoring 90 plus in this subject also. And whenever I am in the past, if I see the past history, there are students who have scored 90 plus in this units in this topic. But then one thing again I remind you that you need to do some calculation practice. It may happen many times that you will solve a question paper of 80 marks, 90 marks, and then you end up with 20 marks. That it happened because of the lack of calculation practice. You think that you are written right, but actually calculation goes wrong. And therefore, in such subjects, you need to have a lot of own practice. Okay. So tomorrow we will see some numericals. Today, actually, I'll give some. Today, just wait for 1 minute. I'll give attendance link. Wait for 1 minute. Meantime, if there is any problem, please ask. Sometimes actually I don't realize whether you understand or not because you don't give feedback. I put one column, one question there in the attendance link, but you very few of you give some feedback. Give me feedback whether you understand everything or not. What I should do to get you understood. Wait for a minute. Not working? Try another link. This link you try. Please try another link which I just now posted. Please reply whether it's working or not now.
Working, sir. Working, sir.
Okay, good.